So hi everyone. So this talk will be more of a survey talk about recent advances in this field, not about one particular work. So let's see. So seeded extractors are these kind of what you usually call an extractor when you don't, explicitly mention what you're saying. And these are falls into the category of the kind of general category of randomness extractors. What's a randomness extractor in general? So this is this function that takes a weak source of randomness in some sense, some random variable that has some amount of randomness in it, usually measured by mean entropy, but it's not really important for this talk. And it tries to transform it or to output a random variable which is close to uniform in statistical distance, which is what our algorithms and protocols usually want and expect. And more concretely, a seeded extractor, which introduced by Nissan and Zuckerman 25 years ago or so, is this function that has this is the only formal thing in the talk. It has two inputs, an n-bit string, which we think of as going to, this will come from the kind of the source of randomness that we are trying to purify, and a second d-bit string, which is going to be kind of an internal randomness for this function. We call it the seed. And it's going to output a bit, sometimes many bits, but for this talk, let's talk about a bit. And this function is called a k-seeded extractor for this parameter k. If for any random variable x that has at least entropy k in some sense, if you look at the output of the extractor, when the randomness is coming from this source of randomness, and when the seed, this extra randomness, is just fixed to some little s, some d-bit string, this thing as a new random variable, right, when the randomness is coming from x, is close to uniform in statistical distance for most values of s, for many s's, for 1 minus epsilon fraction of choices. So let me repeat it in a picture because it's nicer, but you can't do the picture by itself. So say these are the all possible seeds that you have, 0, 1 to the d. And say you have an extractor in mind and a source with sufficient entropy. So entropy k as required by this extractor. Then with that source, you can associate a subset of the seeds. These are kind of the bad seeds. Hopefully the density of, so if this is an extractor, then the density of this set within the big set is epsilon. It's epsilon fraction of all possible seeds. And so what's a bad seed? So it's not a good seed. And what's a good seed? It's anything that any d-bit string that such that if you apply the extractor with that specific d-bit string, you get something which is close to uniform. Okay? So this is the notion of an extractor. There are quite a few parameters and some that I hide, so sorry about that, but this is how it works. And usually the goal is to construct extractors with short seeds. So you want d to be very small. This is the amount of extra randomness that you need in order to extract the randomness from x. You want this to be short. Turns out that log n over epsilon more or less is the right answer. And we have explicit construction that achieve this. And also you want to support low entropy. You want to be able to handle any k. You don't want to assume too much about the entropy of the source if you want to output one bit. And it turns out that the right answer there is independent of n, just log 1 over epsilon. Okay, so it depends only on the error that you're trying to get. Okay, so this is a seed extractor, very well known notion, very well studied. Non-malleable extractors are kind of a very strong seed extractor. So what are these? So this was introduced by Dodis and Vix in a kind of a crypto paper. So we got a lot from the crypto community. And I will give a kind of a different definition, but it's equivalent. And I usually say that this is a nicer definition to work with, but this is the exactly wrong audience to say that, because the original definition had an adversary in it, which I think here is so what? So no, I don't know. I rather don't have adversaries in it. Of course, it's not the right audience to. Okay, anyhow. So what's a non-malleable extractor? So this is a seeded extractor. So already you have this picture of a seeded extractor. But it has an extra property, and the property is that not only it's true that for any seed which is not bad, the output is uniform, close to uniform. What is true is that for any seed that is good, not bad, and for any other seed, so it could be good or bad, so I just put it in the middle here. Even if you condition, if someone gives you the output of the extractor when applied with that S prime, this is still close to uniform. So there's kind of a pairwise independent thing going on. And more generally, you can think of T-wise independent. So you can think of, maybe someone gives you two seeds that are, both of them are different than S. Could be good or bad. And you still want this thing to be uniform even condition, the joint distribution of these two. Okay, so this is the notion of a T non-malleable extractor. This is T equals 2, the standard is T equals 1. Seeded extractors are kind of 0 non-malleable extractors. And non-malleable extractors are newer objects than seeded extractors, which have many applications. So these are less applications, but they have two killer applications. One is for privacy amplification, the original motivation. And the other is the recent breakthrough work of Ishan and David about two-source extractors. Okay, so I hope the definition was clear. If that is the only thing that's been passed, I'll be happy. But hopefully I can do more. So what about constructing extractors, right? Non-malleable extractors are good for these reasons and maybe more. How hard is it to construct them? Well, luckily, and it's not at all trivial, there are non-malleable extractors with great parameters, like essentially equivalent to standard seeded extractors parameters. In particular, you can have seed length, which is important for us, which is logarithmic in n over epsilon, up to constants. And the supported entropy has some dependence in n. I mean, I don't know if it has, but the proof, and also some other proof, shows that there should be some dependence in n, but anyhow, it's very low dependence, so we kind of ignore it. So you can handle essentially any entropy that you want. Now, explicit constructions were kind of harder to obtain, so we worked a lot. And at this point, we have almost optimal constructions. We have so these two works work kind of simultaneously and have roughly the same results. I'll just talk about both of them the same. This is a work of Ishan and Shin, and this is some of mine. So we are able to get almost the right seed length. The supported entropy is the seed length. And this little of 1 is, this log to the little of 1 over epsilon is this weird thing. And now we can also get this tilde, which is kind of better. So we are tilde away from obtaining exceeded extractors, like parameters of non-malleable extractors with parameter much comparable to seeded extractors. But I mean, I'm just trying to give you the kind of the state of affairs. I do want to tell you something about the construction and proof, but that's, these are a bit complicated objects. So I'll try to give you the two main objects.
What's the dependence on T?
Right. So we also have a reduction that says if you have a non-malleable extractor, I can immediately give you a T non-malleable extractor. And then the dependence there, currently it's not good. It's T times the seed length. And initially we thought it should be like T plus, but now we think it could be like log T plus existentially. So it's probably very far from optimal, and it's bad. It's troubling. For privacy amplification, you use T equals 2, so you don't care. T equals 1. But for the two-source construction, T is like logarithmic, so yes. Well, yeah. In the original construction, now we kind of have different constructions that have T equals 10, and you don't care now. Yes. Yes.
Is it necessary that K depends on n?
I don't know. So this is it's a kind of a, well, I really like this question. It's a bit esoteric for these things, but so the original proof of Dodis and Vix had this, and I said it's probably redundant. No one cares. I don't think they even wrote it. It's like log D over epsilon essentially. But then I had another proof that also had disappeared. So maybe it's just something that's there. Maybe not. I don't know. Okay. So let me just give you, if you wake up one morning and you decide you really have to read some papers about non-malleable extractors. Let's see if it works. Yes. So you start looking. It's just very fast because it's and then if you are from this literature of extractors in general, like explicit construction, then you immediately, oh, this is an extractor. I know what it is. They use that thing. Okay. And Raz is another. It's a person, but it's also another extractor related. And okay, so you know that's okay. But then you see these weird little words like this is for correlation breaker with advice, and this is independence preserving merger. So these are new objects that we kind of invented towards these constructions. So let me talk about these a little bit. So starting with this, which actually appeared later. So independence preserving merger. So what's a merger? A merger is a kind of a very well-known object in the literature of extractors, I suppose, kind of non-malleable extractors. So this is it accomplishes a very natural task. So you are given a sequence of random variables, and one of them is uniform. These are random variables for bits. This is how I see them. And one of them is uniform. So I'm happy Golding's modifies. The problem is that the other variables are not necessarily uniform, and you don't know where the good variable is among this sequence. And even worse, there are correlations between these all random variables. And what you want to do, you want to to apply some function, which is called a merger, to merge this in some sense to one good uniform random variable. And of course, you need some extra randomness to do so, but let's ignore this issue. So these are very well known. They have like amazingly beautiful connection to Kakea sets, etc. Probably heard of those. This is why you see many dvirs here. So what's an independence preserving merger? So this is a merger. An independence preserving merger, which we introduced in a different context, but then it kind of, it seems to be also useful for non-malleable extractor. So it's the same picture more or less. You have your set of random variables, but there's also an adversary. And so below is the adversary. And he also has a set of random variables, and they are arbitrarily correlated with your random variables. But for the fact that your good row, your good random variable, by itself, not only by itself is uniform, but actually even conditioned on the corresponding variable here in the second, in the adversary's table. And what you want to do is you want to apply a merger, again with some extra randomness, so that not only the output is uniform, but actually it's uniform even conditioned on what will happen if the adversary will apply the same function to his inputs. So this is what we call independence preserving. You had somewhere independence, and you want to preserve that to the end. So this is one object.
So the nice guy on top is correlated to the blue guys on top, right? But it's not correlated. But it's not correlated to the blue guys on the bottom.
Well,
the smiley guy on top is not correlated to the blue guys on top, on bottom, but correlated on top.
Yes, it might correlate to these extra randomness that you have here, but not to this. Yes.
But the blue guys on top and bottom could be correlated.
Yes. One object. Another object, which is kind of a more weird looking, is a correlation breaker with advice. So here is it's kind of, I don't know, it has a similar flavor. You have a random variable which is uniform, and there is an adversary that has a random variable which could arbitrarily correlate with your random variable. It could be uniform, could be not. And what you want is to just break the correlation. You want to, to transform, using extra randomness, to transform this random variable to a new random variable in which if the adversary will apply the same transformation to his variable, he will get something which gives you no information about the output that you get. Just breaking correlations. So this is a correlation breaker. But of course, you cannot, deterministically, you can definitely not do that because maybe these are the same. Also with extra randomness, I mean, you can do that, but the extra randomness actually could also depend on each other. It's kind of a weird situation. So what you also get is an advice. So what you're given on top of the extra randomness is, someone tells you, well, I have a string alpha, just a fixed string. I think of it as an advice. And the adversary, I know he will use a different string. He has a different one. So your algorithm is allowed to depend on alpha, and you only require that the output is uniform condition on the adversary output, assuming that alpha is different than alpha prime. And usually in the construction, you actually, this kind of the CGL idea, that you actually kind of generate these advices. You kind of, so these fixed strings come from some earlier computation that has been done. So this is a second notion.
Is that carefully chosen alpha? So alpha is something nice, and alpha prime is arbitrarily not equal.
So both of them are just some strings. So but they're different. That's all you know.
But alpha is advice, meaning like not every alpha will do.
No. So the advice is the one bit of information that they are different. That's what I mean. Yes. Right. Yes. Right. Okay. So how much time more do you have? So check.
You have 5 more minutes.
Great. So, okay. So, with these two objects, let me just give you kind of the big picture. The technical big picture. So, it's not like a conceptual. Okay. So, there was these two great problems, like super great, two source extractors and privacy amplification against active adversaries. Dodis and Vic showed that actually, non-malleable extractors suffice to actually completely solve this problem, right? But you just need to construct those. And then David and Ishan showed that, with such frequent work, showed that actually, if you have these optimal, then you actually have optimal two-source extractor as well. This is a kind of an improvement of Amnon Tashma, Ben Aroya, and Din Doron from Tel Aviv, building on Ishan, David, and other results that were there. So non-malleable extractors are kind of, I try to put it in the center suggestively. It's kind of in the heart of the matter for two different problems. But okay, how do you construct optimal non-malleable extractors or any kind of non-malleable extractors? So it turns out, it's kind of in retrospective, that you just need a way to break correlations. Once you know how to construct the second object that we talked about, using a reduction by the CGL paper, I call it, you have this. Okay, this is the heart of the problem now. But how do you construct a correlation breakers? It's not easy. So the original way was to use this flip-flop primitive, which is essentially a correlation breaker when you know that you and the adversary get just one bit of advice. But if you get more bits, it's harder to follow that advice. It's a longer advice. It's more noise. So yeah, there was a very non-trivial reduction here. But how do you construct the flip-flop primitive? So you just do it. It's not going to continue. But the technique being used is alternating extraction, which was, if I remember correctly, was introduced in the crypto setting. So it's and was used also by Dodis and Viggs. And alternating extraction makes use of seeded extractors. And this I can blow up to another big picture like that. Okay, but now we know something better. We know that we can kind of bypass this flip-flop. It's kind of it has a high cost to make it. This error has high cost, relatively. So now we have this new notion of slightly newer notion of independence preserving merger. So we are able to actually use that to construct correlation breakers, non-malleable extractors, and that's it. And we construct these also using this technique, but in a slightly weaker way. And this newer work that I mentioned at the end. So previously, what you did, you kind of start with some correlation breaker and some independence preserving merger, and you kind of obtained using this independence preserving merger a slightly better correlation breaker. It gets a correlation breaker as input, and you have this procedure to transform that to a better one using the independence preserving merger. And just you kind of repeated that at the end. You got, if you want to use the correlation breaker, you have to kind of make some recursive calls, go back for. But then in these newer works, we kind of figured out that it's a friendly relation. So you can actually construct better independence preserving mergers using correlation breakers. And actually, correlation breakers also play a role in this error, in the work of in the new work of Amnon, Dean, and Avi. So it's really kind of in the heart of the things. And we know that seeded extractor has many applications. They do like for PRGs and least decodable codes and whatever. And the question is, can you find other big boxes that you can use non-malleable extractors for? Yeah. Thank you very much.